You guys ready for a joke again?
Yeah.
Okay, this won't take long. It won't take much out of your day. And it might be funny. You ready? Here we go. A boy asked his father, "What's the meaning of a solar eclipse?" Father replied, "No, son." Hi everyone, today we're going to do an extension of our reflected ray lab. This one is applying the law of reflection instead of demonstrating it. So it's still found in the same spot in your textbook. This is on page 194 specifically. And I got ahead and just got my piece of paper ready to go. So what I've done is I've just gotten a blank piece of paper. Careful, Nora.
So go.
Blank piece of paper, and I've traced in the middle of it the straight line to represent my mirror. Now, I think it might be a good idea if we drew our normal lines first this time, because there's nothing crowding our diagram, and this will give us a target basically to put in our rays. Okay, so I kind of got it all set up to go. Just got to follow the instructions, which starts off similar to our last lab. I'll talk about that, but I'll show you a more finished product in a minute. Okay, so before the diagram gets a bit complicated, I'm just going to show you one incident ray completed along with its reflected ray drawn in. Now I got two incident rays coming from point A of the diagram, or of the object, but only the first one that's hitting with a 21-degree angle, the angle of incidence, I have the reflected ray drawn for. So you can see that the reflected ray bounces off of that mirror surface also with the same 21-degree angle. Now that's theory, that's the law. So we're going to be applying this law throughout our other three incident rays, and then we'll extend our reflected rays back into the mirrors or behind the mirror and see where they intersect, the pairs of them, and that will be an indication of where the object will be. Okay, so I'm just going to continue to do the other three incident rays, or three incident rays along with the reflected ray cousins, and then I'll show you what that looks like before extending them. Okay, so there's all my reflected rays coming from each of my incident rays. There's 4 pairs of rays in total. The two coming from point A of the object are hitting at 21 and 31. You can see the reflected rays are bouncing off at those same respective degree angles. We just spin around. On the other side of the object, this is coming from point B. We have 23.5 and 31-degree angle incident rays. And you can see that the reflected rays bounce off at exactly that same angle. Okay, so now all I have to do is extend my reflected rays only into the mirrors behind, and wherever they intersect each other from each point A and B, that will be where the image is located. So that'll be the next thing you'll see. Okay, so the diagram is now complete. I got my reflected rays, dotted lines just to make them different looking, extended behind the mirror. So there's the pair coming from point A, really, of the diagram. They connect over here. Okay, we'll talk after. No? Now point B of the mirror's reflected rays kind of come into the mirror on this angle. You can see it labeled up above. Now there's a little bit of error here. I'll just take a different point of view for it. But it looks like a pretty neat diagram, just that the image seems to be a little further in behind the mirror than what it would be in real life. Again, we're going to experience some error with pencils, the small piece of paper that we're dealing with, tiny little mirror. But, you know, again, we're trying to demonstrate our law and apply the law of reflection, which is really all stated here with these angles again. Okay, so I'll get the ray box out, show you how it looks, and we'll just be almost. So I got the ray box lined up on our first incident ray. You can see it's the 21-degree angle one, and you can also see the mirror is reflecting that light right along the predicted ray that I had. Okay, now if we get the camera like this, you can also see the extended reflected ray, which is a real one from the light itself, going in behind the mirror surface, okay? So it all does line up and not prove, but show that the law of reflection is being held true. So I'm just gonna quickly do the others, do a quick little check. I'll show you a little snapshot of them all in picture form, okay? Okay, so there's the 31-degree angle, looks pretty good, maybe a little bit off. Here's the 23.5 degree angle. Again, everything looks pretty lined up, pretty good. Nice to sneak a little view into the mirror itself. Yeah, it looks nice there.
Yeah.
And the last ray is the 31 degree angle on the other side of the object. And you can see there's a bit of an error on that one. So that may account for some of the skew I have in behind the mirror from that point, that same point B. Okay, but everything looks pretty good. Okay, so here's the end result. We have our object, which is ironically a Barbie doll mirror, laying in front of our other real mirror. And I just focused on that so you can see that the image of the Barbie doll mirror is in the actual mirror itself right now. Now we're supposed to see how well our diagram lines that up in terms of a real image versus the fake image. Okay, so it's a little hard to do here in a video, but we're kind of just seeing, okay, does that image appear to be where I think it is? Okay, yeah, I think my object's a little further than it should be from the mirror surface based on my drawing. But again, not a bad job. And just to show you, mirrors, mirrors, and mirrors. There's a way for us to see infinity if we line it up correctly. That's pretty good. Well, you got a long face?
Yes.
How come?